Every second, over 1 billion neutrinos produced in the sun go through 1 square centimeter of your body. That's the size of your thumbnail. My nails look awful right now. But what are neutrinos? Neutrinos are subatomic particles on the standard model of particle physics, which is kind of like a periodic table, but for the subatomic particles. The neutrinos are in the lepton class, of which there are 6 different particles. 3 of them are neutrinos. They have 3 different flavors: electron neutrino, muon, and tau neutrino. Something interesting is going on with the neutrinos though. In the standard model, they're predicted to be massless particles. However, they do something pretty interesting that makes us prove that they actually do have a small but finite mass. This interesting property is called neutrino oscillation. Let's use an example. The sun. We were just talking about how neutrinos come through your body. Well, in the sun, only electron neutrinos are made. Physicists figured out that this was actually due to neutrino oscillation. The neutrinos are actually changing flavor when they reach the Earth. Neutrino oscillation is very similar to something we already know: the model of a coupled oscillator. 3 pendulums, 3 flavors. With coupled oscillators, we have normal modes. These are oscillations that the system prefers to be moving at. The normal modes for the triple pendulum coupled oscillator is this, and this. When we talk about neutrinos, we aren't talking about normal modes. We actually call them mass eigenstates. A particle is not just a particle. It also acts as a wave. We have 3 different types of mass eigenstates. However, it's really rare that they'll be in those exact eigenstates. It's usually a superposition of the eigenstates. A good way to think of the superposition is thinking about waves that are similar but slightly different. We have a 150 Hz sine wave and 150.5 Hz. If we put them on top of each other, we get the effect called beating. This beating can represent something in neutrino oscillations. When we have the bigger amplitude, it is an electron neutrino. However, when we have the smaller amplitude, we have a muon neutrino. The beat is the electron, and the space in between is the muon, just depending where we measure it. But how can we measure how it changes in time? Linear algebra. Let's go back to our example of the sun. If we have our electron neutrino eigenstate, we can transform it into the 3 mass states to find how it changes. The transformation matrix that we use for neutrino oscillations is so important that it actually has a name. It's such names. Pontecorvo-Maki Nakagawa Sakata. Pontecorvo-Maki Nakagawa Sakata. Okay. The Pontecorvo-Maki Nakagawa matrix. You know what I'm gonna do? I'm gonna say the PMNS matrix and have it on the bottom. The Pontecorvo-Maki Nakagawa Sakata matrix. Hey, no! Or the PMNS matrix is the transformation matrix that we use to change basis. This is the PMNS matrix. It's pretty scary, right? It's different from the one that we use for oscillatory motion because it's unitary, and we can prove that it's unitary. First, we take our original matrix, multiplying by its Hermitian conjugate, and seeing if the solution is the identity matrix. In the case of the PMNS matrix, it looks something like this. Here's the original, the Hermitian conjugate, and we see an answer that's reminiscent of the identity matrix. If we normalize by dividing each column by the sum of itself, we get our identity matrix. This proves that the PMNS matrix is unitary instead of orthogonal, as is the case for the mass spring system. There is a much nicer and more compact way of writing the steps that we need to do though. It's this right here. What we need to do is know that C is the change of basis, the dt is the time evolution, and the c to the -1 is our basis change back. Once we do this, we can figure out how the neutrino oscillations change in time. All this math proves that neutrinos oscillate between flavors. If neutrinos can oscillate between flavors, that means that neutrinos must have mass. Neutrinos, even though they're small, are actually really important. Neutrino oscillation won the 2015 Nobel Prize for Physics. Thanks for watching! I hope you enjoyed learning about neutrinos.